Welcome folks, welcome to today's discussion. Today we shall discuss about dielectric capacitors. Now what is a capacitor? In a sentence, actually a capacitor is a system that can store electrical charges. How are they made? The simple construction consists two conducting plates, and we can give them charges like plus Q and minus Q. There is no hard and fast rule that this should be plus, this should be minus, anything. And due to the accumulation of charges in these conducting plates, the potential phi is formed between the plates, and there is a relation between this accumulation of charges and this potential. Actually Q varies directly to this phi, like Q is equals to C phi. C is the proportionality constant, which is called the capacitance of the capacitor. Now we are not concerned about the basic theory of capacitors here, like the detailed construction, the energy stored, the combinations, parallel and series combination, and etc. and etc. We are constrained about this dielectric capacitors. For the basic theory of capacitors, I shall make a separate video. Now, here we shall discuss about three types of capacitors, like parallel plate capacitor, coaxial or cylindrical capacitor, and spherical capacitor. As you know from the thumbnail that it is the part 1 of our lecture. In this part we shall discuss about only this parallel plate capacitor. Actually capacitors are very important in electrostatics. So I have divided this lecture into two parts. In our second part we shall discuss about these two types of capacitors. Before I further proceed, if you are new to my channel, then don't forget to subscribe and of course turn on the notification bell to get the regular updates. Okay, let's back to our lecture now. So this is a simple parallel plate capacitor. These two are our conducting plates, and this thing is the dielectric between the plates. Epsilon is the permittivity of this dielectric. Let the area of the plates be capital A, and the thickness of this dielectric is small d. That is, the distance between these two plates is small d. Now here is a catch. This small d must be very small in respect of the dimensionless of this capacitor. Why? Because in parallel plate capacitors, this effect, this fringing effect is very common. See, these lines are showing the uniform electric field between these two plates, but at the end there is some distortions. See, these are the distortions. This is very common for parallel plate capacitors. It is called fringing effect. Okay, now we are calculating entire calculation, thereby neglecting this fringing effect. So small d should be very small compared to the other dimensions of the capacitor to neglect this fringing effect. Otherwise the fringing effect will come into play with a very non-neglecting term. Okay, now we shall use E is equals to sigma by epsilon. Now if I take this as a positive x direction, then we can add I cap, or we can just simply use the magnitude of E is sigma by epsilon. Now this E is equal to sigma by epsilon comes from the fact that for a charged plate the field is sigma by epsilon. It comes from the application of Gauss's law for charged plates. And what is sigma? Sigma is just the surface density of charges. Now, as we all know, E equal to minus d phi dr. So phi equals to integration minus E dot dr. Now, in our second step, we just altered this lower and upper value because this minus should be here plus. Now integration 0 to d sigma by epsilon dr is very easy, sigma d by epsilon, and putting sigma equals to q by a, we have phi equals to q d by epsilon a. Half of our calculations have been done. Rest is applying this q is equal to c phi, that is c equal to q by phi. Okay, so here is our c equals to q by phi, that is from this epsilon a by d. Okay, now this is one method. There is another method also. Let's come to our alternate treatment. Before I start, I advise you to know all the treatments for every type of calculations, because you don't know when you use this equation or this equation. You should know both the methods so that whenever you need something, you can use this method or this method. Okay, now in this method or in this treatment, we shall use Laplace's equation, del square phi equals to 0. See, it is a dielectric material, and if we don't add any free charges from outside, then free charge density is equals to 0 ideally. So we can write del square phi equals to 0. Again, we are using one-dimensional Laplace's equation. Why? Because we are concerned about only the x-axis. Now let us take that phi 1 and phi 2 be the two potential at x equals to 0 and x equals to small d. So we shall apply our one-dimensional Laplace's equation here, like d2 phi dx2 is equals to 0. Okay, this implies phi equals to ax plus b, where a and b are constants. Now our boundary conditions are at x equal to 0 phi equals to phi 1, and at x equals to d phi equals to phi 2. Now putting these boundary equations, we can get phi 1 equals to a into 0 plus b and phi 2 equals to a into d plus b. So solving these two equations, we can have that b equals to phi 1 and a equals to phi 2 and phi 1 by d into x. It is very easy calculation and I know you can do it. Now we have phi equals to this form, just putting the a and b values here. Now e equals to minus d phi dx. So differentiating with this with respect to x, we have only phi 2 minus phi 1 by d, and this one is 0. Now there is some step jump because of this minus sign. I have included this and make this thing as a positive quantity, thereby altering this 2 and 1. So e is phi 1 minus phi 2 by d. Again, we know that e equals to sigma by epsilon. Okay, so sigma by epsilon equals to phi 1 minus phi 2 by d. Now putting value of sigma here, q by a, we can easily rearrange the whole equation as q by phi 1 minus phi 2 equals to epsilon a by d. See, everything is done. So c equals to q by phi 1 minus phi 2 equals to epsilon a by d. So both the equations give us same result, only the method are different. Okay, now let's proceed to some special cases like air capacitor. What is an air capacitor? The area or the space between those plates are only air, so epsilon becomes epsilon naught and rest become the same, that is C equals to epsilon naught A by D. Okay, now what is our case 2? This is very important. Capacitor with a non-uniform dielectric. What is non-uniform dielectric and what is uniform dielectric? Our first case was uniform because K or the dielectric constant was independent of the distance between the plates, that is X. But now it is non-uniform. Non-uniform means the dielectric constant of the material will depend upon the distance. And like what? In simple case, we can take K is equal to mx plus n. It is a linear combination. Okay, we don't go to some more complex cases. This is the most common and most simple case. So this is non-uniform dielectric because K here varies with X. See, everything is same, only the dielectric has been changed from uniform to non-uniform. Okay, so our boundary conditions are at x equals to 0, K equals to K1, and at x equals to D, K equals to K2. So putting these boundary equations in this K equal to mx plus n, we can have K1 equal to n and K2 minus K1 by D equals to m. So we can put these two in here. So K becomes this one. Okay. Now the field at any inside point can be written as E equal to sigma by epsilon. So epsilon is epsilon naught into capital K, and this capital K can be written from here. So epsilon become this type of. Okay. Now we shall calculate phi, and the method is same, minus integration d to 0 E dot dr. Keeping making this minus plus, we can alter the limits like 0 to d, and we just put this value here. So this integration becomes like dx by x, and the answer is ln x. Now here K2 minus K1 by D is the coefficient of x. So the result becomes 1 over this K2 minus K1 by D, that is D by K2 minus K1 ln of the whole thing. Now I am quite sure that you can easily calculate the lower value and upper value, thereby putting those limits here. So I am just jumping to our this relation. I know you can do it. If you have any problem in deriving those equations, you can comment me and I shall send you the PDF notes. So we can find that phi equals to QD by epsilon, this type. We have already have our phi. So C equal to Q by phi. So Q by phi equals to epsilon naught K2 minus K1 into A by D ln K2 by K1. So this is the form of non-uniform dielectric capacitor. It is more or less the same. See this epsilon naught A by D, but with some K terms due to this non-uniformity. Okay. Now there is one more case, that is composite dielectric. What is composite dielectric? See, there are two dielectric materials stacked together. This is 1 and this is 2. So according to our picture, we have to determine our boundary. Now let us take that this is x equal to d1, this is x equal to d1 plus d2. So the width of this number 1 dielectric is d1, and for the number 2 the width is d2. Okay, so now we have for 1 E1 equals to sigma by epsilon 1, and for 2 E2 equals to sigma by epsilon 2. Now the integration comes. See, here is one more boundary. Okay, so the integration will not be the same like the before. First we shall go from this d1 plus d2 to d1. See, lower value d1 plus d2 to d1. Then we shall go from d1 to 0, d1 to 0. So there is two different integrations, and putting the values of E1 and E2 from the above, we can easily evaluate the equations, and rearranging them we can get sigma by epsilon 1 d1 plus sigma by epsilon 2 d2. We know that sigma equal to q by a, so the whole thing becomes phi equal to q by a into d1 by epsilon 1 plus d2 by epsilon 2. So we have got our phi. Now C equal to q by phi, that is epsilon naught a by d1 by k1 plus d2 by k2. Now composite dielectric means only two? No, there may be several dielectrics like 1, 2, 3, 4, etc. and etc. So there should be some general equation like this: epsilon naught a by sum over I di by ki. I may be 1, 2, 3, 4, 5, 6, anything. It may be n number of dielectrics stacked together like this. So d1 by k1 plus d2 by k2 plus dot 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 dn by kn and so on. This is very important equation for your mathematical purpose. Now what if we have this? What is this? See, this is actually an air capacitor, and I have just put a dielectric substance of with T in such a way that it is not composite, not uniform. But we can use this composite dielectric equation for this one also, because we can write d1 as T and d2 as d minus T. Okay, so we shall use this method to find the ultimate C. See, sigma by epsilon 1, in place of d1 we have written T, and in place of d2 we have written d minus T, and this is just the rearrangement. So we have C equals to epsilon A d minus T plus T by K. Now it is very clear that composite dielectric formula is very useful for this type of special cases. Okay, this is just a special case of this one, so you need not to cram this one, but you have to remember this equation. It is very much important. Now these are all mathematical steps. What about the physical significance? See, in our previous cases we have C equals to epsilon naught A by D or epsilon A by D, whatever, epsilon naught A by D, but here D by K. Here also some modified form of D by K. So the denominator is lower than our previous results, and as a result the whole C will increase, because this thing is lower than our previous result. So C increases if we add the dielectric, whether be it composite, whether be it non-uniform. So the physical significance is the capacitance increases with the introduction of dielectric material within the plates. Actually it has also its commercial importance also, because air capacitor have epsilon naught A by D, but if we introduce different dielectrics the charge storing power, that is the capacitance, increases, and that can we can make it of commercial use. Okay, so this is the end of our discussion today. If you like my video, then please give us a thumbs up, and please share your valuable comment at the comment box. Thanks for watching, guys. See you soon.